Okay, so we'll begin. Are there questions?
Sir?
Yes, go ahead, please.
Yeah, you were saying yesterday that like at the end we have a given Lagrangian for that describes our observations, right? In the sense that once we have fixed the non-free part, let's say lambda phi to the power 4 part,
Yes.
that is what describes our universe once and for all.
Yes.
And that is true for all fields like Klein-Gordon field, Dirac field, and whatever we want to add to the Lagrangian.
Exactly. Yeah.
So in general, there will be many such parameters, some lambda 1, lambda 2 associated with different fields and particles.
Yes.
So isn't it possible that our physical observations can be governed by multiple sets, like different values for lambda, the set lambda 1, lambda 2, lambda 3, as in there is an ambiguity in the values of lambdas and the parameters which are not observed.
Yeah. See, the point is that we have infinite number of observations in principle, right? Whereas the number of such parameters is finite because you have a finite number of fields. Okay, because there are finite number of particles that we see in nature. So in that sense, you have infinite number of observations, and you only have a finite number of parameters to fit.
So, why do you say we have infinite number of observations?
Because you can calculate the scattering. As I said, the main observations in particle physics are scattering amplitudes. Of course, particle masses are one of them. But scattering amplitudes mean that you collide two particles and you observe what happens as a result of the collision. Okay, which means that you calculate the probability of finding a set of particles going out at certain angles, and those angles are continuous variables. So using that, you have actually infinite number of data, infinite amount of data to fit, right? Because you can ask for the probability of finding certain number of particles at some particular angle. Right? You can change the angle, the number is different, and that also you can calculate. So in that sense, you have infinite number of observations. Okay, and only a finite number of parameters to fit.
So we only work in theories where we can actually fit this data.
Yes, exactly. So standard model is that theory.
Okay. And also regarding renormalizability, what we were saying earlier, that let's say 5 to the 6th theory is not renormalizable because we need infinitely many observations to compensate for the divergences.
Yes, exactly. Because once you include the 5 to the 6th theory, right, you may say that okay, you have just added one more parameter.
Yeah.
But then what you can show is that in order to get a sensible theory, you have to add not one parameter, but infinite number of parameters, because the coefficient of 5 to the, you have to add also 5 to the 8 term, 5 to the 10 term, and all the way to 5 to the infinity.
Okay. So but just 5 to the 4 is enough.
Yeah, 5 to the 4 is good enough, right? 5 to the 4 is renormalizable. Whether that is enough for experiments is another matter. But it is enough for renormalizability. And it so happens that the standard model that describes our universe is a renormalizable quantum field theory. Okay, that's why you have finite number of parameters with which you can try to explain everything.
All right.
Any other question? Okay, so let me then proceed. So let me remind you what we did yesterday. So we defined this Green's function G plus, which is the vacuum expectation value of the product of phi x1 and phi x2. And then we inserted a complete set of states between phi x1 and phi x2. And from that analysis, we derived a certain set of relations. And the final form of the relations that we had arrived at is here. Okay, so G plus x1, x2 is given by a Fourier transform of some function f of q. And f of q is given here, okay, in this line, where you have a sum over complete set of states in the theory, okay, and then you have a delta 4 of Pn minus q, okay, and then this matrix element. And then we also said that by inverting this first relation, you see that it depends only on the difference x1 minus x2. So if we set, for example, x2 equal to 0, okay, and do the inverse Fourier transform, we can write f of q in terms of g plus in this way. But of course, our strategy will be that you will first calculate fq using this, and then from there you will find the expression for g plus. Now we'll prove two results about fq. So the first result is that fq is Lorentz invariant. What we mean precisely by that is that f of lambda q should be equal to f of q, where lambda is any arbitrary Lorentz transformation matrix. The second property that we'll try to prove about fq is that fq vanishes whenever q is space-like, and independently of this, whenever q0 is less than 0. So we'll see how to prove these two relations, okay, using the relations that we already have here. So are there any questions on this? Okay, so this is what we had arrived at yesterday. Okay, so if there are no questions, I'll proceed.
Sir?
Yes, go ahead, please.
Q is the conjugate variable of x.
Well, q is just a variable that you introduced, right? You can say it's a Fourier transform variable of g plus.
Yes, so if there are conditions on q that q is space-like, it should space-like are x1 and x2, right? How can the Fourier transform variable be space-like?
Well, space-like basically means q square is positive. That's what we mean by a space-like vector. If you don't like this notation, right, this is not space, okay? But a space-like momentum, right, is one whose square is positive, right, which means p0 is less than mod p.
Oh, okay.
So this is just a notation, right? What we mean by space-like vector is when for which q square is positive.
Oh, okay, so there are no actual light cones here.
No, you can draw light cone on this in the p space also, right? Which are not light cones in the way we think of light cone in position space. Okay, but don't think about light cones if you don't like it, right? If you try to associate light cone with position space, right? Forget about light cone, right? All we are saying is that q square. So you can just ignore this statement. Okay, I'll use the space-like momentum to denote momentum vectors with q square positive. But if you don't like the word space-like, just think of this, right? That fq should vanish when q square is positive.
Okay.
Okay, so this space is certainly not the ordinary space that we are familiar with. Is this clear?
Yes.
Okay. Any other question? Okay. So let's try to prove these relations first. So first, let's try to see how to prove that f of lambda q is f of q. And for this, we are going to use this relation. Okay, the fact that f is a Fourier transform of g plus. Okay. And we recall that we had proved earlier, okay, using Lorentz symmetry, that g plus is Lorentz invariant. Okay, so what did we prove exactly? We proved a relation of this kind, that if you take the vacuum expectation value of phi of lambda x1, phi of lambda x2, these are, you can think of this as phi tilde of x1 and phi tilde of x2, but phi tilde corresponds to Lorentz transform phi. So we have proved that the vacuum expectation value of phi of lambda x1, phi of lambda x2 is the same as vacuum expectation value of phi of x1, phi of x2. And this translates to a relation on g plus, because this is g plus lambda x1, lambda x2. So this implies that g plus of lambda x1, lambda x2 must be equal to g plus of x1, x2. So now let's try to analyze f of lambda q. Okay, because we are trying to prove that f of lambda q is the same as f of q. So to analyze this, so f of lambda q, then in the expression for f of q, I just replace q by lambda q, right, which is here. And the way we will now proceed is that I first make a change of variable from x to x prime. Okay, so I write x equal to lambda x prime. Now when you do that, we know that the Jacobian of transformation is 1 because determinant of lambda is 1. So d4x is the same as d4x prime. Okay, we can integrate over d4x prime without any additional factor. Here x is replaced by lambda x prime. Okay, so this becomes lambda q dot lambda x prime. And here x is replaced by lambda x prime, so g plus of lambda x prime. Now we use the fact that the inner product, this is the Lorentz invariant inner product. So inner product is invariant on a Lorentz transformation. So lambda q dot lambda x prime is the same as q dot x prime. So I replace it by e to the minus iq dot x prime. And because g plus is Lorentz invariant, okay, by this relation, okay, you can set x2 equal to 0 on both sides. We get g plus of lambda x prime 0 is the same as g plus of x prime 0. Okay, so we arrive at this expression over here. And this, of course, is the same as f of q. Okay, because x prime is an integration variable, so you can change the name from x prime to x, and that becomes f of q. So this proves that f is Lorentz invariant. That f of lambda q is the same as f of q. Are there questions on this? Okay, so we proceed. So next, we are going to try to prove that fq vanishes for q square positive. And also independently of this, that for q not negative. So let's first prove this. Okay, that fq is 0 whenever q naught is negative. So to prove this, let's look at the expression for f of q, this top expression. Okay, so you can see from here that in order that f of q is non-zero, there must be some pn for which pn and q are equal. Because if pn and q are not equal, then of course the delta function is 0. So in order that the f of q is non-zero, there must be some pn for which pn is equal to q naught. Now, if q naught is negative, that means that in order for this to be non-zero, there must be some state n for which pn0 is negative. Okay, because pn0 has to be equal to q0. But we have assumed that the vacuum has 0 energy. Okay? Remember that we assumed that all the Lorentz generators P mu annihilate the vacuum. And because vacuum is the lowest energy state, there is no state with pn0 less than 0. And this is the proof that f of q must vanish for q naught negative. Because if q naught is negative, then this delta function always gives 0. Okay? Because there is no pn for which pn naught can agree with q naught. Is this logic clear? Any question on this? Okay. So let me then proceed. Now we have to prove that fq vanishes for space-like momentum, for q square positive. And here you are going to use a property of the Lorentz transformation, that if q square is positive, okay, q square positive means what? That it means that q vector square is larger than q0 square. So if that is the case, then there is a property of Lorentz transformation that it is always possible to find a Lorentz transformation that makes q0 negative. So q itself may have q0 positive, but it's possible to find a Lorentz transformation that makes the transformed q negative. And for that, of course, f of q has to vanish, because you have already proved that f of q must vanish for q0 negative. And then using the fact that f is Lorentz invariant, right, that f of q and f of lambda q must take the same value, it follows that f must vanish also for the original momentum, okay, for which q0 might have been positive, but for which q square is positive. Okay, so that by Lorentz transformation, you can make q0 negative. So this finishes the second part of the proof. That fq vanishes also for q square positive. Okay, or for space-like momentum. Are there questions? Okay, so if not, let me proceed. So what have we learned so far? Okay, here is a summary. So you have learned that G plus is given by a Fourier integral of this kind, of f of q. And then you have learned these two properties of f, that f of q is Lorentz invariant, and that f of q vanishes for space-like momentum, and also for negative q0. So using these two properties, we can write an expression for f of q, which I have given here. 2 pi is just a normalization. This is purely a matter of convention. Okay, we'll see why I have introduced this 2 pi. And then we are saying that f of q must be a function of minus q square because of its Lorentz invariant. So it should be a function of q square only. And because this vanishes for space-like momentum, that means you see, it is non-zero only for time-like momentum. You can also multiply by h of q0 without violating Lorentz invariance. And this guarantees that q naught is always positive. Okay, this is a Heaviside function, okay, which vanishes for q0 negative and is 1 for q0 positive. So this is the most general form of this function f of q that you can write down based on these two properties that we found here. So this small f is a new function of one variable only. See, capital F was a function of 4 variables. But now by using these properties, you have made it into a function of one variable. And this one variable function also has the property that it vanishes for negative u, which in turn will mean that this will vanish for positive q square. So this form guarantees that f of q vanishes for positive q square, as well as it vanishes for positive q naught, so for negative q naught, and that it is Lorentz invariant. So all the properties that is encoded in 1 and 2 can be summarized by writing f of q in this form. Okay, are there questions or comments? Okay, so given that f of q has this general form, we are now going to substitute this in the expression for G plus. And here is the result. Okay, this is a direct substitution of this in the expression for G plus. Okay. And now we are going to write it in a slightly more complicated way, okay, but it will become clear why you have written it this way. Okay. Can you hear me? I just got a message saying that the internet connection is unstable. Did you miss any part of the lecture?
Your voice got a bit morphed, so.
Okay, so should I repeat some part? Okay, maybe I can say it again, okay, or at least summarize what I have said. Okay. So what we have said here is that using these two facts, that f of q is Lorentz invariant and f of q vanishes for space-like momentum, okay, we can write down this most general form of f of q, okay, in terms of a function of a single variable. Okay, small f of u is a function of a single variable, and this function has the property that it vanishes for negative u. And now what you are going to do is to substitute this in the expression for G plus, and this is the expression for G plus that we got. Now what you are going to do is to write this in a slightly more complicated way. Okay. I'll write this G plus as an integral over a new variable, over an additional variable u. Okay. So I write this G plus x1, x2 as integral 0 to infinity du. Okay. And then in this integral, I'm going to replace f of minus q square by f of u, okay, and multiply by a function of delta u plus q square. And you would notice that I really haven't done very much, okay, because if you carry out this integral over u, okay, you will see that u equal to minus q square, and that will give us back f of minus q square h of q naught, okay, which is what we had to start with. So this just looks like some additional complication that I have introduced, but soon it will become clear why I have written it in this form. So to see this, we have to remember the form of the same two-point function, but this time for a free particle of mass m. So suppose you had a free particle of mass m, okay, the free Klein-Gordon equation. We did calculate this quantity in the free Klein-Gordon field theory, and instead of calling it G plus, we called it delta plus, and that delta plus had this form. So here what I have done is that I have written the argument of delta plus as x1, x2, but also the mass parameter that is there in the theory. Earlier I hadn't written down the mass, but now I'm also displaying explicitly the dependence on the mass of the particle, the mass parameter. So that had this structure. And now let's compare this with this. So what we see is that this f of u, of course, can be taken out, okay, because this doesn't depend on q, so you can take it out. You can write an integral du f u, and the rest of the integral, are the same. The only difference is that the u is replaced by m square here. So using this, we can write g plus in this neat form, that it's integral 0 to infinity du f u times delta plus of x1 x2 root u. Okay, why root u? Because here you have delta of u plus q square, here you have delta q square plus m square. Okay, so this u is to be identified as m square. Okay, so here, since the argument was m, I'm calling it delta plus x1 x2 root u. So it's as if g plus that you see here is a superposition of free particle results for different masses root u with weight f of u. Is this clear? Any question on this? Okay. So if there are no questions, I'll proceed. So this function f of u is called the spectral density. It's called the spectral density because as if you have a spectrum of particles, I mean the two-point function is behaving as if you have not just a single particle of mass m, but a whole spectrum, in fact continuous spectrum of particles of different masses given by root u. Okay? And the weight factor is given by f of u. But soon we'll see that this is not the correct interpretation. Okay, but nevertheless it's called spectral density because it's as if G plus can be regarded as a superposition of this spectrum of many particles with many masses, but continuous family of masses with weight factor f of u. Is this clear to everybody? Okay, so let me proceed. So this is again what I have said, okay, the same thing. The G plus looks like it's a superposition of free particle results for different masses. But now we all use this result to now calculate G. Okay, so what was G? G was the time ordered product. Vacuum expression was the time ordered product of operators. Okay, and the reason that we are looking at G is because G is something we know how to calculate. Right? The perturbation theory that we developed was not for calculating G plus, okay, but for calculating G. So let's see what it says for G. That's not very difficult because G x1 x2 is given in terms of G plus. Okay, it's a step function x1 h of x1 naught minus x2 naught times G plus x1 x2 plus h of x2 naught minus x1 naught times G plus x2 x1. And now if you substitute this, okay, I again got a message saying that the internet connection is unstable. So can you follow what I'm saying?
Yeah, your voice cracked a bit, but I think it's fine.
Okay. Okay, so G is given by this. Okay, and now if you substitute the expression for G plus that is given here, okay, it's a straightforward algebra, and what we get is that G actually is given by the same superposition, okay, integral du fu of delta f x1 x2 root t. Okay, instead of delta plus you have delta f, and that's not a surprise because the relationship between delta plus and delta f is the same as that between G plus and G, because G is given by this and delta f is also given by a similar expression with G plus replaced by delta plus. So the idea is that we know how to calculate G x1 x2, okay, at least in perturbation theory, but even non-perturbatively G x1 x2 is usually easier to calculate than G plus. And so the idea is that if we know, since we know how to calculate G x1 x2, we can use it to extract this function f of u, okay, the spectral density. And typically what one finds is that f of u in fact is non-zero for all u above some value. So the naive interpretation, okay, which is what I was giving you earlier, is that as if you have a continuous spectrum, okay, not spectrum of single particles with a definite mass, okay, but a continuous mass spectrum, okay, of all masses, okay, with weight factor given by f of u. But this is not the correct interpretation, okay, of the theory, and we'll see this in more detail later perhaps. But what it really implies is that this G plus, okay, or G, okay, but let's look at G plus, which was more fundamental in some sense, that we are introducing the sum over states in the middle, right? Sum over n. So what this is saying is that G plus actually receives contribution not just from single particle states, but also from multi-particle intermediate states. So for multi-particle intermediate states, these have the property that the p square can take continuous values. And that's what we are really saying in this. Okay, the fact that it looks like we have continuous masses, okay, or the continuous p square values, okay, where a single particle state has p square equal to minus mp square. Okay. The fact that we are seeing a continuous p square values, okay, is because G plus has contribution from multi-particle intermediate states. So let me just explain how it works. Okay. So let's suppose that mp is the physical mass of the particle. Then if you take a two particle state, then let's calculate the p square of a two particle state. Okay, and suppose our individual particle momenta are p1 and p2. So p square is given by p1 plus p2 square, okay, which is here. P1 square of course is minus mp square, p2 square is also minus mp square because these are particles of mass mp. But 2 p1 dot p2 is given by this, and this in fact, as you can see, can take any arbitrary value because p1 and p2, not any arbitrary value. Okay, I'll say what value it can take, because you see p1 and p2 can vary continuously. Now to see this a little more clearly, we can always go to a frame in which p2 is at rest. Okay, so let's suppose, because p square is Lorentz invariant, right? It doesn't depend on which Lorentz frame you are using. So let's suppose you have gone to a Lorentz frame in which p2 is at rest. Okay. So that means p2 vector is 0. Okay. So this term is just mp. Okay. This is 0. Okay. And here you get square root of p1 square plus mp square. So what we have here is minus 2 mp square minus 2 and then square root of p1 square plus mp square times mp. And you can easily convince yourself that this is always less than minus 4 mp square. Okay. But it can take any continuous value, any value below minus 4 mp square. Okay. So if such states contribute to the intermediate state in the sum over n, okay, then that would mean that f of u will be non-zero for all u above u equal to 4 mp square. Okay, because u is actually equal to minus q square, right? If you remember the notation, because of this delta function, u and minus q square are related. Okay, and q in turn is equal to pn, okay, by the other delta function that we had here, okay, from here. So this is carrying information about what particles, what are the intermediate states that are contributing to this sum. Okay, that's what this f of u, small f of u, is capturing. So in contrast, if we recall free Klein-Gordon theory, there G plus is the same as delta plus. In this sum, you can easily convince yourself that only the single particle states contribute. Okay, there is no contribution from multi-particle state because phi has a single A or and single A dagger. Okay, so only single particle state can contribute in this sum. So this is the main difference between an interacting theory and a free theory. That in an interacting theory, a two-point function of this kind, okay, of phi 1, phi, the two-point function of two phi's, maybe I have not written it here, a two-point function of two phi's can get contribution from multi-particle intermediate states, okay, which doesn't happen for a free Klein-Gordon theory. Are there questions? Is this clear to everybody? Okay, so if there are no questions, we'll proceed. So now we turn to the question that we had posed last time. Okay, I'm just trying to see if I can connect my iPad. No, I think our internet is still down, so we have to live without the iPad today. Okay, so let me try to understand how we can possibly extract the physical mass of the particle from the knowledge of Gx1, x2, right? Because this is a question, if you remember, this is a question we had posed last time, right? And in fact, one of the main goals of this analysis that we have been doing since yesterday was to find a procedure for calculating the physical mass MP. So the strategy that you are going to follow is the following. See, so far you have been completely general, right? We have not made any approximation anywhere, right? That we have analyzed that this form that we have gotten, this form that you have gotten, or this form that you have gotten is completely general. It's true. We haven't made use of perturbation theory, or you have not made use of what are the intermediate particle states that are contributing are single particle states or multi-particle states, or not even doesn't even have particle interpretation, right? This is always the general formula for Gx1, x2. But now we ask the question that what would happen if there are single particle states of mass MP? What will be their contribution to Gx1, x2? So this is what we'll try to calculate. And the idea is that once you understand how single particle states contribute to Gx1, x2, then we'll look at our expression for Gx1, x2 that we have found using perturbation theory and see how to extract MP from there. Okay, because you will know how which part of that Gx1, x2 is coming from single particle states. Okay, so that's the general philosophy that we are going to follow. So for this, we begin by assuming that the p mu eigenstates contain single particle states of mass MP, which means that there are states with Pn dot Pn or Pn square equal to minus MP square. And now let's proceed and analyze the contribution to G plus from these single particle states. Okay. So this contribution, now we are not talking about the full contribution to G plus, but only part of the contribution that comes from single particle states. Okay. If there are different particles of different masses, then this will be repeated for every single particle state separately. Okay, and then you can add up their contributions. Okay, but right now let's assume that there is a one kind of particle mass MP, and we are trying to calculate their contribution. Okay. So this is given by the sum over sum prime. This prime on the sum basically means that you are summing only over the single particle states. And now using the fact that the single particle states can be labeled by just the spatial momentum P, because the energy is fixed in terms of the spatial momentum by this formula, okay, EP squared of P square plus MP square. I can write this in this form. So remember, yesterday we said that the sum over n, okay, with the normalization that we are using, becomes integral dq p over 2 EP, okay, in the for single particle state. So that's the normalization I have used here. Here, instead of Pn, I have written P, okay, with the understanding that only the spatial part of P is independent variable. P0 is given by this EP. And now here you have omega phi 0 P and P phi 0 omega, okay, as we had earlier. So this denotes a single particle state of momentum P, mass MP, and energy given by EP. Okay, are there questions? Is this clear to everybody so far? Okay, so let me proceed from this. Okay, so now I make a claim, okay, which I'm going to prove, that this matrix element, omega phi 0 P, okay, and of course its conjugate, the other one is its conjugate, okay, these matrix elements that appear here, this is independent of P, okay, which means given two different momenta, P and P prime, okay, we have omega phi 0 P is equal to omega phi 0 P prime. And so let me proceed with the proof. Okay. So let's suppose that we are given a single particle state P. Then for any other momentum which is nearby, let's say, okay, so first of all, let me state the following result, that if you have two arbitrary momentum, both referring to the same single particle, okay, so both referring to single particle of the same mass MP, okay, then it's a general result that there is always a Lorentz transformation that converts one to the other. Okay. Because the fact that they are single particle states basically means that the P square is the same, right, and P0 is positive. So if there are two vectors P and P prime for which P square is equal to P prime square, and if both P0 and P prime 0 are positive, then it follows that there is a Lorentz transformation that takes one to the other. So given two single particle states, you can always find a Lorentz transformation that takes one to the other as long as they have the same mass MP. Now suppose that these are nearby. Okay, suppose P and P prime are infinitesimally close to each other. Then these two states will be related, these two momenta will be related by a infinitesimal Lorentz transformation. And then we can use this fact, okay. Remember yesterday we had used this fact that P prime, okay, so P prime vector means that it's a single particle state carrying momentum P prime. This means that you start with a single particle state of momentum P and then you apply the Lorentz transformation matrix operator, okay, which is here. And yesterday we had said that we choose the normalization, that the normalization that we have used for P is such that P prime, that means with P with that this is the defined momentum, okay, single particle state is the same as if you had started from the single particle state of momentum P and then apply the Lorentz transformation on it. Okay, so P prime by definition is this one. Okay. So you had chosen our normalization of P in such a way that this relation holds. Okay. And you are now going to make use of this. Okay. And see, it's because of this relation, right? It's because you wanted this relation that you have to have this 2EP inside. Okay. Otherwise, you would have had just dqp. Okay. We are forced to introduce this 2EP in this integration measure, okay, because you wanted to preserve this relation. Okay, and then now we are going to make use of this. So is this clear to everybody? Okay, that this relation that we derived yesterday, or do you want a reminder of how it came? Okay, so since there are no response, I am assuming that it's clear to everybody. Okay. So let's now try to use this, and we'll use this to calculate this quantity, omega phi 0 p prime. There is one more relation that you have to use, and that's this commutator between G and phi. This is also a relation that I had used last time. Okay, in fact, yesterday, that J nu tau commutator phi x is given by this. And here now, if you set x equal to 0, you get the commutator of J nu tau with phi 0 is just 0. Okay, because this x nu and x tau makes things vanish. So that's simple. Now we proceed. Okay, and we also have this relation, right? That J mu nu omega is 0, because we have assumed that the vacuum is Lorentz invariant. So now we try to compute this object, okay, omega phi 0 p prime. For p prime, I substitute this. So you have omega phi 0 and then this operator acting on p. The first thing we do is to use the fact that the J and phi commute to take this operator on the left of phi. Okay, so that's here. And then I use the fact that omega J mu nu is 0. Okay, that's here. To simply set this term to 0. So you are left with omega phi 0 p, and that's what you wanted to prove. Right? So omega phi 0 p prime is the same as omega phi 0 p. Okay. This we have proved for infinitesimal Lorentz transformation. Okay. But once it holds for infinitesimal Lorentz transformation, you can also establish that this holds for finite Lorentz transformation, because any finite Lorentz transformation you can build by applying infinitesimal Lorentz transformation many times. So what this tells us is that this quantity that is appearing in this expression for G prime plus, this actually is a constant. This doesn't depend on P. So we'll find a way, we'll parameterize this constant by some Z, which is a constant over 2 pi q. Okay, and that's what we have done here. Okay, this 2 pi cube is again just a matter of convention. Okay, we could have called this Z, okay, but we will see that this will have some useful role to play. Okay, so we'll call this constant Z over 2 pi cube. The important point here is that Z doesn't depend on P. Are there questions? So the main idea is that we'll try to substitute this form in the expression for G prime plus that we had here, and then see what simplification we get. Okay, so here is the expression for G plus. Okay, it is the same expression as what we had here. Okay, this one. Okay, I think this is the same expression as that one, except that I have written it in a slightly different way. This should have been a G prime plus, okay, not G plus, because you are talking about contribution, the single particle contribution. Okay, so G prime plus has this expression. Okay, and you also have seen in the last slide that this combination is a constant, which I am parameterizing in 1 over 2 pi cube times Z. So if you substitute this, we get G prime plus as Z over 2 pi cube times this integral. Okay, this whole complicated object just become a constant, 0 over 2 pi cube, and you can take it out of the integral. Now we can try to write it in as a 4-dimensional integral by introducing this d4p. Okay, but of course, once you have introduced an integral, extra integral, you also have to introduce a delta function. Okay, so I introduce d4, an extra factor of dp0 times delta p0 square minus ep square. But that, of course, is the same as 1 over 2 ep, right? Because once you do the p0 integral, you will get back 1 over 2 ep from here. And this HP naught guarantees that we pick only the P0 equal to plus EP contribution and not P0 equal to minus EP contribution. Okay, from when you do the P0 integral. Okay. And it will also set P0 equal to EP in this exponent which of course was understood here. Okay, even though I wrote it as e to the I p dot x1 minus x2, it was understood that the energy component P0 is not an independent variable, but it's given by EP. In this form, you can take P to be independent variable because this delta function will set P0 equal to EP. Is this clear, this line? Okay. And now we notice that this line over here is nothing but delta plus x1, x2 MP. Because let's look at the expression for delta plus that we had written down earlier. Yeah. So this was delta plus x1, x2 M. Okay. There's a 1 over 2 pi cube 4 here and 2 pi here. So it's a net factor was 1 over 2 pi cube. Okay. There's a delta of q square plus m square h q naught. Okay, and integral d4 q to the I q dot x1 minus x2. Okay. It's exactly the same expression that we have arrived at here. Okay. Except that here you have an MP. Okay, and instead of integration d over q, I have integration over p. So this is then given by z times delta plus x1 x2 MP. So what we learn is that a single particle contribution to the 2-point function g plus x1 x2 takes a form that is similar to the field theory expression delta plus, except that m is replaced by mp, which is the mass of the single particle, and there is a possible normalization constant z that is multiplying delta plus. Otherwise, the single particle contribution is as if you have a free field of mass mp. Is this clear? Okay. So now let me remind you what our goal was. Right? Our goal was to see what the single particle contribution is to f of u, right? Because we had parameterized g plus by this. So let's compare the expression that we have gotten here with the expression, the general expression that we had found, which takes into account all contributions, right? Single particle as well as multi-particle contribution. So by comparing this with this, right? Here you have an integral du fu delta plus x1 x2 root u. Here you see the g prime plus is given by z times delta plus x1 x2 mp. So by comparing this with this, we see that the contribution of the single particle state to fu can be written as simply z times delta u minus mp square. Because you substitute z times delta u minus mp square here, you set e equal to mp square, so that you get back delta plus z1 z2 mp, and of course z factor just multiplies it. So this equation here that we have found for the single particle contribution to G plus is equivalent to saying that single particles contribute to f this expression fs of u, which is z times delta u minus mp square. Multi-particle contributions are quite different. So this is the feature that we will now use to identify which part of the Green's function that we calculate in perturbation theory or by any other means captures information about the mass of the particle. Namely, we look for contribution to FSU that is proportional to delta of u minus mp square. And whatever the argument of delta function is, will tell us what the physical mass of the particle is. Is this clear? Are there questions? Okay. If not, let me proceed. Okay. Now, again, as I said, that ultimately we cannot, I mean, what we can easily calculate is not G plus, but G, right? The time order product. So let's try to now translate this to what it means for G. Okay. So that's not very difficult. So let's look at the expression for G and we see what it means for G. Okay. So G in terms of F is given by this expression over here. And now we see that if f of u has a contribution proportional to z times delta u minus mp square, its contribution to g x1 x2 is given by this integral plus these are the multi-particle states or whatever other states there may be. Okay, they may not even have particle interpretation, right? We don't know whether they have particle interpretation or not. But the single particle contribution is here. Okay, if there are single particle states of mass mp, that gives this contribution. So that's z times delta f x1 x2 mp plus contribution from other states. Okay. And now we are going to translate this to momentum space Green's function, because that's what we'll really analyze to extract the mass of the particle. So g tilde p on p2, let me remind you, is the Fourier transform of g x1 x2. So it's given by integral d4 x1 d4 x2, then e to the minus I p1 dot x1 p2 dot x2 g x1 x2. So now we substitute for g x1 x2 this z times delta f x1 x2 mp plus the rest, okay, contribution from other states. And now we know, so this part you see after you have taken out the z, right? This is just the momentum space Green's function for free Klein-Gordon theory, okay? Except that the mass is replaced by mp. Okay, it's not the mass parameter that was there in the Klein-Gordon action, but it's the physical mass mp, whatever it may be. So then this integral will be given by the same form that we had for free Klein-Gordon theory, the propagator of the free Klein-Gordon theory in momentum space, except that here the m has been replaced by mp. So then g tilde p on p2, okay, the contribution to g tilde p on p2 from the single particle states is given by z times the propagator for the single particle state in free Klein-Gordon theory, okay, with m replaced by mp. Okay, I over minus p on square minus mp square plus I epsilon. So what this is telling us, okay, is that a single particle state of mass mp actually produces a pole in g tilde at p on square equal to minus mp square. Okay. So that's a concrete statement that we'll try to make use of. Okay. So what we learn from here, okay, is that if somebody gives you, okay, a way to calculate this g tilde p on p2, okay, and we have seen how to calculate this, at least in perturbation theory, okay, then what we need to look for, okay, in order to find the physical mass of the particle, okay, not the mass parameter m that entered the Lagrangian, okay, but the actual physical mass of the particle, is the location of the pole in this Green's function. Okay. After you have stripped off this 2 pi to the 4 delta 4 p1 plus p2, is just momentum conserving delta function. Okay. We have to look for where the poles are located in g tilde. Are there questions? I again got a message saying that the internet connection is unstable. So is there any part that you have missed? Okay, as long as I'm not hearing anything, I'm assuming that everything is okay and I'm proceeding. So this is what I have said here, that we can look for single particle state of mass mp. So what he sees that the single particle state of mass mp produces a pole in g tilde, but we can also reverse it by saying that we can find, by finding the pole locations in g tilde, we can find the mass of the particle. Okay, and this is the physical mass of the particle. And we will now try to do this in the next 2 slides. I'll try to describe how to do this in perturbation expansion. But before I go on to do that, let me just mention that this analysis that you have done actually goes through for 2-point function of any pair of scalar operators. So the point is that I started by saying that we will analyze the 2-point function of phi x1, phi x2. Here, right? We started by saying that we look at the 2-point function of phi x1, phi x2. But suppose instead of phi, I had some operator O1. right? Suppose O1 x1, O2 x2. O1 and A2 are some scalar operators. They could be phi square, phi cube, box phi, right? Or box phi whole square, anything. Then if you follow this analysis carefully, right, you will see that nowhere in this analysis we have really used the fact that I am using the field phi itself. Nothing about phi that we have used, okay, is telling us that the phi actually is the fundamental field of the theory. So you could represent this, you could replace this analysis for any pair of operators. Okay. In particular, if the scalar operators, then there is no change at all. Okay. If there are some other tensor operators, like for example the derivative of phi, right, del mu phi or del mu phi, then there will be some small change. Okay. But for scalar operators, the analysis will be identical. Okay. And you will come to the same conclusion, okay, that in the two-point function, okay, or if you calculate the time ordered product of two-point function of some scalar operators, that if you calculate, for example, a time in a matrix element of this kind, okay, and then you take a Fourier transform, okay, in x1 and x2 to write down the in the P1 P2 variable, then the locations of the poles, okay, in the P1 square plane, okay, will contain the same information, okay, the mass of the elementary particles. So phi is nothing special, not special here. Okay, I am using phi here because that's what you have learned how to calculate in perturbation theory. Okay? But you have in fact also learned how to calculate this in perturbation theory. Okay? So you could look for single particle states in this matrix element as well. Okay? And this is important because in many cases, okay, we really have to do this. Okay? And just to give an example, right? Suppose we have electrodynamics, right? We have not introduced electrodynamics yet, but let's imagine that we have a similar theory of electrons and positrons and photons, and you are looking for the mass of the positronium state. Okay, positronium is the bound state of electrons and positrons. If you calculate the two-point function of electron positron, then because electron and positron are both charged objects, the positronium will not contribute in the intermediate state. Okay, in this analysis, see here, for example, suppose we are doing this for electron-positron system, and this was the electron field, this was the positron field. Okay. Then in this sum, okay, positronium will not appear because electron has positive charge, it has negative charge. Okay. Positronium has no charge. Okay. So this matrix element will be 0. Okay. So look for the mass of the positronium, okay, by using the same formalism. We cannot use either the electron or the positron operator, okay, but you have to use composite operators, okay, like the electron-positron pair operator, and similarly the product of the electron field and the positron field. Okay. So that's why this is a more general result than what you have emphasized, and I am emphasizing it now, okay, that this analysis goes through for two-point function of any pair of scalar operators. Okay. That for any pair of scalar operators, if you look at the Fourier transform and look for the pole in the momentum space, okay, the location of the pole contains information about the single particle spectrum in the theory. Are there questions?
Would the order of the pole remain the same?
Yes, order of the pole remain the same because there is nothing here. You see, it will remain the same. Why? Let me explain that. The pole came because, okay, see this relation, right? The fact that it was 1 over mp square plus mt square came from here, or came from a delta f, right? Okay, so why did we get delta f or delta plus? Okay. If you follow this carefully, right, this has nothing to do with the fact that we had a single phi, okay, because all we needed was that this was constant, right? If you replace phi by phi square, okay, this fact that prove that this remains a constant still holds, okay, and that is good enough to show that it is proportional to delta plus. Is that point clear?
Yeah.
So if you had a phi square and phi square, right? Then the single particle contribution in the intermediate state will have exactly the same form. Okay, Z will change. Okay? And in certain circumstances, Z may vanish, right? And that is the example that I gave for the electron-positron pair, right? The corresponding Z for the positronia will vanish. But otherwise, the analysis goes through. As long as Z is non-zero, you will get the pole of the same order. Okay, because you will get delta plus. Even though you are starting here with phi square, okay? This delta plus is not dependent on the fact that you had a phi square or phi cube here, right? It depends on the fact that this quantity is a constant. Okay, that's all that went in showing that this is delta plus x1, x2, m. Is this point clear? If you just follow the notes carefully, right, you will see that I have not used anywhere the fact that phi is an elementary field. Okay, that if you replace a phi by phi square here, for example, right, you will get a similar relation with phi replaced by phi square. Okay, because the transform of phi square, okay, is given by the same form. Okay, that only depends on the fact that phi square transforms as a scalar, just like phi transforms as a scalar. Okay? So it will still vanish when x is equal to 0. Okay, and you can follow the same procedure.
Yeah, that is fine. But like we could also check the same if we had some simple composite operators like phi square and phi 4. We can break it down into delta f x1 x2 and like multiplication of propagators.
True.
So wouldn't that increase the order of the pole?
Yeah, see, it will increase the order of the pole in perturbation theory. It will look like it's increasing the order of the pole in the perturbation theory. Okay, but ultimately you have to look for contributions of this kind, right?
Yeah.
Okay, so that I mean this contribution, right? So what will happen is that if it will not give just poles, but there will also be branch cuts and so on, right? Because there will be multi-particle states. The singularities that will get a lot will be of different kinds. Okay? But
Yes.
the pole part will not change. Because where in this analysis, right, will you see a double pole, for example? Right? Unless it so happens that a multi-particle states contribute double pole, right? But that doesn't happen, right? You can check also what the multi-particle state, two-particle state will contribute. Okay? And what one can show, they'll contribute branch cuts, but not double poles, for example.
Okay.
So in momentum space, right? Even if you do Feynman diagram, right? So order of the pole will increase in the sense that they are in the integrand will have more factors in the denominator.
Yeah.
But you also have to do a loop integral, right?
Yeah.
And what you are saying here is that after you have done all the loop integral and so on, if there is a pole, it will be single poles. But of course, there will also be other kinds of singularities like branch cuts and so on.
All right.
Okay, are there other questions?
Sir, can there be multiple poles?
Multiple poles. Yes, so if there are, for example, different kinds of particles, right? Of different masses, then each of them will contribute poles, right? So there will be multiple poles.
Okay. And why should bound state, sort of positronium state should contribute a branch cut? I mean, what I'm trying to think is, like bound states have sort of a discrete spectrum.
Yeah, so bound states will not contribute branch cuts. So
Okay.
in the if you look for the positronium state, right, in electrodynamics, right, they'll contribute poles. Two particle states which are not bound, right,
Okay.
they will contribute branch cuts. Two particle states of this kind, right,
Yeah.
what we discussed.
The one
Yeah.
you showed.
These will contribute branch cuts. But positronium will contribute
Okay,
poles,
yeah.
right? But you have to look for the correct channel, right? In the electron positron 2-point function, it will not contribute poles because it just doesn't appear in the intermediate state, right? The Z will be 0. And that's why you have to look for composite operators, and in that channel it will contribute poles.
Yeah.
Any other question? Okay, so in the last, I think I have about 20 minutes. So let me try to now explain how we actually go about doing this in perturbation theory. So when you try to do perturbation theory, I have to now introduce some new notions, okay, some new notations. So we'll introduce the notion of truncated one particle irreducible Green's functions. Okay, so these are two different aspects. Okay, so let me explain what these mean. So truncated Green's function basically means that you just remove the external propagator factors like this. Okay, so in every Feynman diagram, right, we know that there are external propagator factors like this. Okay? So you just remove those. Okay, that's what one means by truncated Green's function. So after you have written down the expression for the Feynman diagram, you just factor those out. 1 pi means that we are summing, instead of summing over all Feynman diagrams, we sum over only a subset of the Feynman diagrams. So which subset? We remove all Feynman diagrams which have the property that they fall apart into two disjoint parts by cutting one internal propagator. And here for the 2-point function in 5-4 theory, I have given some examples of what we mean by one particle reducible diagrams, okay, which are not one particle irreducible. This diagram is not a 1 pi diagram because by cutting this propagator here, it falls apart into two parts. This diagram is not 1 pi, right? Because by cutting this, it falls apart into two parts. Similarly, this one is not 1 pi. Here are diagrams that too represent 1 pi diagrams, right? Because this one, for example, it doesn't, there's no internal propagator that you can cut, which makes it fall apart into two parts. Here, there is, you can cut 3 internal propagators to make it fall apart into two parts, but not one, right? Similarly, here, you cannot cut one internal propagator and make it fall apart into two parts. So these are called one particle irreducible diagrams, okay, where these are one particle reducible diagrams. So is this notation clear? So this is just to classify different kinds of Feynman diagrams. Okay. And it's useful not only for 2-point function, but also for multi-point functions. Okay. But let's now, for the time being, focus on 2-point functions only. So now,
what do you mean by truncating that part?
Pardon?
Like just ignore it, like the truncation part.
Yeah, just ignore this factor, or divide out by this factor. That's what you mean.
But on what grounds are we doing that?
No, we are just defining it, right? We are not going to try to change our Feynman rules. Okay. So the idea is that we will write down the full Feynman diagram, okay, in terms of this truncated 1 pi Green's functions.
Okay.
Okay. Not that you are trying to change the Feynman rules. Is that clear?
All right.
Okay. So this is just a definition, right? Some intermediate stage. Okay. So we'll define by this quantity I sigma p1 square. So this means sigma is a function of p1 square. It is a function of this argument. Okay. This will be defined to be the sum of all truncated 1 pi 2-point Green's function without this delta, momentum conserving delta function factor. Okay, that's the definition. So here are the examples of contribution. This I've already said. So maybe if I had my iPad, I could have written down some expression, but I'll I'll say in words. Okay, let me see if I can log in again. So I think unfortunately our internet is still down, so I cannot log in. Okay, so let's look at this expression. Okay, so this, what is the contribution to I sigma p1 square? Okay. So there is a loop momentum L flowing in this loop, right? So there will be integral d4 L over 2 pi to the 4. Okay. And there is a propagator I over minus L square minus m square plus I epsilon. Okay, that's propagator. So L is the momentum that is flowing in this loop. Okay. And then there's a factor of minus I lambda over 4 factorial from this vortex. So these factors are included in the definition of I sigma. Okay. But you don't include the I over minus p1 square minus m square or I over minus p2 square minus m square, okay, from these two external propagators. Now, nor do we include this momentum conserving delta function 2 pi to the 4 delta 4 p1 plus p2. Similarly here, okay, let's say which are the factors we'll be including. Okay. There's a 1 over 2 factorial. Okay, by the way, I should have said the combinatoric factor, of course, is included in the definition of this. So here there'll be 1 over 2 factorial because there are two vortices. Then minus I lambda over 4 factorial square. Okay, one from each. Okay. Then there is I over minus L1 square minus m square from here. I over minus L2 square minus m square from here. And from here it will be I over P1 minus L1 minus L2 whole square plus m square minus I epsilon. Okay. So those are the three factors that will come from these three propagators. And then you have to integrate over the two loop momentum, right? Integral d4 L1 by 2 pi to the 4, integral d4 L2 by 2 pi to the 4. So that's a contribution to the I sigma p1 square. Similarly here, right? It will be basically the square of this up to combinatoric factors. So is this clear how to build I sigma p1 square? Any question on this? Okay, so as I already emphasized that this is just a definition. Okay, I'm not changing the Feynman rules. Okay, I'm just defining I sigma p1 square to be this. Okay, because our goal will be that we'll write down the full propagator. Okay, full 2-point function, not a full 2-point function. Okay, which contains all of these diagrams in terms of this I sigma p1 square. Okay, and here it is diagrammatically. This is how I will represent it. Okay, so this one is that's the usual propagator, right? I over minus p1 square minus m square plus I epsilon. This one, okay, now this diagram includes everything, right? It includes the 2 pi to the 4 delta 4 p1 plus p2 factor, the propagators I over minus p1 square minus m square plus I epsilon here, I over minus p2 square minus m square plus I epsilon here, and then the sum of all of these, I'm calling I sigma p1 square. Okay, so this blob, this is not a Feynman diagram. This blob over here with I sigma p1 square written in the center means it's the sum of all the Feynman diagrams that come here, but only the 1 pi Feynman diagrams. So is this notation clear? Okay, so this is the same as sum of all of these. But now we have this diagram. This diagram, again, I sigma p1 square by definition is the sum of all of these. Okay. But this represents a one particle reducible diagram. Okay, whereby cutting this propagator, it falls apart into two parts. Okay. So this, for example, includes diagrams like this. Okay. Because this is a contribution to I sigma p1 square. This is a contribution to the second I sigma p1 square, which is here. Okay. Similarly, this is a contribution to the first I sigma p1 square. Here, this one is to the second one. Here, this one is to the first one. This one is to the second one, right? So if you write this expression for I sigma p1 square, okay, and write down this, right? This basically means that you can choose here any of these diagrams, and independently of that, you can choose here any of these diagrams. Okay? So all possible combinations appear here. Okay? Of course, one has to make a little effort to make sure the combinatoric factors work out correctly. Okay, but one can check that they do work out correctly. Okay? And the Feynman diagrams of these kinds, okay, can be encoded in this compact form by writing it this way. Now, this of course doesn't stop here, right? Because you can have three independent one particle irreducible components. Okay, that will correspond to, for example, a diagram like these two, and then another bubble coming here. Okay, that will be part of the third diagram, third part. Okay. Similarly, if you had another bubble in the center here, okay, that will also be part of the third diagram, and so on. So are there questions on this? Is this clear what this means, these diagrams? Okay, so what I'm going to do now, okay, is to write down the actual algebraic expression for this. Okay, and that makes things a little more clearer. So here is the expression for G tilde. Okay, this is the sum of all Feynman diagrams. So each of these diagrams, of course, have 2 pi to the 4 delta 4 p1 plus p2 that I take out. Then this term represents this one, I over minus v1 square minus m square plus I epsilon. This one has two factors of I over minus p1 square minus m square plus I epsilon. Normally, I would have written it as I over minus p1 square minus m square plus I epsilon, I over minus p2 square minus m square plus I epsilon. But of course, because of this delta function, p1 square and p2 square are the same. So I have just written it as I over minus p1 square minus m square plus I epsilon whole square times this, which is I sigma p1 square. This diagram has three factors of I over minus p1 square minus m square plus I epsilon. One from here. By momentum conservation, this carries the same momentum as this one. And the third one from here. That's why there's a Q. And then you have the square of I sigma p1 square, because there is I sigma p1 square factor coming from here and I sigma p1 square factor coming from here. It's the same momentum p1 flowing through, right? This one as well as this one. So that's why these are the same. And then there are higher order terms which have the same structure, right? Next term will be a fourth power of this and a cube of this. Next term will be a fifth power of this and a fourth power of this, and so on. So is this clear? This organization of these diagrams? Okay. So you see at the end that even though I introduce I sigma p1 square, ultimately we are interested in this one, right? I sigma p1 square is just an auxiliary quantity in terms of which we can express this in a neat form. Okay. And here is that neat form. Okay. So the claim is that this sum is actually the expansion of this in powers of sigma. Okay. And it makes sense to expand this in powers of sigma, okay, because you see that if you look at the expression for sigma, right, it always has a factor of lambda, right? This has lambda, this has lambda square, this has lambda square, and so on. And because you are assuming the lambda is small in terms of which you are doing the expansion, right, it does make sense to expand out things in powers of sigma. Okay, and so the perturbation theory gives an expansion in powers of sigma, okay, which is here. Okay. But you can also resum this whole series, okay, to write it as a single neat form like this. Is this clear? Okay. It requires a little algebra, right? It's a binomial expansion of 1 over 1 plus x, roughly, right? You just take out I over minus p1 square minus m square common, and then you have 1 plus sigma over minus p1 square minus m square plus I epsilon. Okay. You have to invert that, right? Because it's in the denominator. And that gives you, so 1 over 1 plus x, you write expand as 1 minus x plus x square minus x cube, and so on. And that's this series. Okay. The alternate plus minus sign comes because of the i's. Okay, there's a this is I cube, right, which is minus I. This is I to the 5, which is the same as I, and so on. That's why this 1 minus x plus x squared, that's where it comes from. So is this clear? So now you see why we introduce the sigma in the first place, right? Because we can write the expression for the G Green's function neatly in terms of the sigma. And furthermore, because we have said that MP is the location of the pole in the minus p1 square, right? that by definition, what the physical mass is determined by saying that the Green's function has a pole at p1 square plus m square equal to 0. p1 square plus mp square equal to 0. So to find the location of the pole, you have to basically set this equal to 0. So that leads to this equation mp square minus m square plus sigma of minus mp square equal to 0. Okay, because that's the location of the pole. And the residue determines z, right? Because it's supposed to be iz over minus p1 square minus mp square plus I epsilon. So the z is determined also by from the residue at the pole. Okay, but let's look at the mp. So this equation looks like a complicated equation because sigma is in general a complicated function of mp. But in fact, we can solve it iteratively because sigma is small, right? Sigma has already a power of lambda. Okay? So if you are trying to find mp in a perturbation expansion, it is more advantageous to write this equation in this way. Right? We bring this m square and sigma of minus mp square on the right hand side and write this as mp square equal to m square minus sigma of minus mp square. Okay? And now, because sigma has an expansion in powers starting at lambda, at order lambda, okay, we can try to solve this iteratively. Okay? Then we will treat sigma as small and solve this by iterative method. Okay, Newton's method of iteration. So leading order solution is mp square equal to m square. Okay, which is of course not a surprise, right? Because if you are doing perturbation theory, then the leading order better be what you are calling mass of the particle earlier, right? In the free Klein-Gordon theory. So leading order mp square equal to m square. Next order mp square equal to m square minus sigma. Here mp is unknown, but we'll substitute for mp the leading order solution. So mp square equal to m square. So in the next order will be mp square equal to m square minus sigma of minus m square. Next order will be mp square equal to m square minus sigma. And now in the argument, you have to replace by minus m square plus sigma of minus m square. Okay, because you had a minus mp square, right? For mp square, we'll substitute the second order solution. And this you can again further expand by writing it as sigma of minus m square plus sigma prime of minus m square times sigma of minus m square. Okay, and you can proceed this way. And so to any finite order in lambda, right? It's a finite computation, right? You have to do a finite number of iterations to find the expression, the relation between mp and m to any finite order in lambda. So basically, this is the procedure that one uses to find mp in terms of m and lambda. Now, as I have already emphasized earlier, that this relation is divergent, right? Because sigma has divergences, right? All these diagrams that you see that contribute to sigma, these are all divergent. So in that sense, it's not really that you can calculate mp in terms of m. But what it allows you to do is that once you regulate the divergence, then it gives a relation between mp and m, okay? But that relation involves that ultraviolet curve of lambda, capital lambda. And then you have to carry out this procedure for renormalization. Okay? So that helps us in expressing other physical quantities in terms of mp at the end. Okay? If you had a finite theory, then this would actually allow you to calculate mp in terms of the parameters of the theory. Okay? Then you start with a Lagrangian with some parameter m, and in a finite theory, it will, this procedure will tell you systematically how to calculate mp in perturbation theory as a function of m and lambda. Okay, so I think I'll stop here. Are there questions?
So at the end, m does not have physical significance, right?
Yeah, m does not have physical significance. Yes, that's true.
Like, then how would we like make use of this expression in the sense that mp we'll have to anyway observe. We cannot fit in a like feed in a value of m to get mp.
Yes, true.
Then
Yeah.
how is this useful?
The way we will make use of is that we will now calculate the scattering cross section, right? Those will also be given as functions of m and lambda.
So there we'll replace m and lambda by like one of them by mp.
Yes, and the other one by some other observable.
Okay.
Okay? And then we'll get an infinite number of relations between the rest of the variables.
And if the theory were not renormalizable, we would encounter an inconsistency.
Well, there you will find that you need infinite number of parameters, right? So then you keep eliminating and you never, there's no end to it.
Yeah, but at this expression state, like at this expression, we cannot say the theory is not renormalizable.
No, not at this stage, right? So basically, okay, I can give you the general rule, okay, that the theory is renormalizable if the coupling constants all have dimension, all have positive dimension, or positive or zero dimension.
I don't know what that means.
You don't know what that means? Okay. So let's suppose you have, so we have said h bar equal to 1. Okay. So the mass dimension and length dimensions are inverses of each other.
Yeah.
That you're familiar with, right? Okay. So you calculate the mass dimension of various fields. Okay. How do you calculate the mass dimension of various fields? That you look at the Klein-Gordon field, right? Integral d4x and then d phi whole square, right? That's the kinetic term.
Yeah.
So using that, you can determine that phi has mass dimension 1. Because x has mass dimension -1, right?
Yeah.
Okay. So d4x has mass dimension -4, right? The derivatives of mass dimension 1, so that gives you 2. So phi has to have mass dimension 1, so that it becomes dimensionless. Action has to be dimensionless.
Yes.
Okay. Now with that, now if you calculate the dimension of lambda,
yeah,
then because it's lambda phi to the 4, right? d4x has mass dimension -1, -4, phi has mass dimension 4. So lambda has to have mass dimension 0.
Yeah.
Okay. If you had a lambda phi to the 6, then phi to the 6 has mass dimension -6, right?
Yeah.
Okay. Sorry, mass dimension 6, and d4x has mass dimension -4. So lambda would have to have mass dimension -2. Whenever that happens, then the theory is typically not renormalizable. Okay, it comes from some counting. Basically, whenever that happens, that basically means that the more lambdas you use, okay, you have to compensate by putting more powers of momentum in the numerator. Okay, because lambda has mass dimension, negative mass dimension, and more powers of momentum you put in the numerator, the more is the divergence, right? Because divergence is coming from large momentum region.
Yeah.
Okay, so that's the general rule of thumb. Okay, there are some exceptions, but the general rule of thumb is that whenever you have a coupling constant of mass dimension negative mass dimension in the theory, then the theory is not renormalizable.
Okay.
Okay, are there other questions?
Sir.
Yes, go ahead, please.
Yeah, I was asking, even after renormalization, the value that we get for lambda, that should be small, right?
Yes, indeed.
Because, otherwise, the way we are approaching this problem would break down.
Yes, certainly.
I mean, we are using perturbation theory and it should be small.
Okay, maybe I should, that when you actually carry out the procedure for renormalization, right, what you will find, okay, either there is a way to write down this whole formalism, okay, so that the expansion, okay, is not in terms of lambda. Okay, lambda is the parameter that enters the Lagrangian, okay, but the expansion is actually in terms of the renormalized coupling constant, which is finite. Okay. So here, the way you are presenting it, that we have a parameter lambda in the Lagrangian and we are expanding in powers of lambda, right? But it is possible to reformulate the theory. Okay. So the expansion is actually an expansion in powers of the physical 4-point coupling. Okay. That you calculate by taking, say, 2 scattering at certain angle. Okay. So from that you can extract the physical 4-point coupling, and you can reformulate the perturbation expansion as a power series in that coupling. Okay. So in that sense, what the Bayer coupling is doing, right, is not relevant, because this is actually the relationship between the Bayer and renormalized coupling is infinite anyway. Okay. That is not the way I have presented it here, and I mean, but you will learn it when you actually carry out the renormalization procedure. Okay. That how to do this, so the expansion actually is in the expansion in powers of renormalized.
Okay.
which are all finite.
Sir, but I think he's just asking whether the perturbation theory we have carried out is valid in the sense that the parameters are small. But that we already know, right? That it's not like the perturbation series. We even though we truncate it, it's
Yeah.
not really convergent.
No, I think that is another point. Okay, whether the convergence, okay, whether the perturbation theory actually is convergent is a different point, right? But I think there is a point which comes even before that, okay, which is that the relation between lambda, okay, and the physical couplings has some infinities, right? Because it involves a cutoff, right? I said that m and lambda are not finite parameters anyway, right?
Yeah.
So what are you expanding in, right? If m and lambda are infinite, right? I mean, you're expanding in powers of infinity. But what the way to avoid this confusion is that it is possible to reformulate this perturbation expansion, okay, not in terms of m and lambda, but in terms of some renormalized mass m, right, which you can take to physical mass or something else, okay, and a renormalized coupling lambda, right, which is related to some physical 4-point scattering. Okay. Those are small, right? Those have to be small in order for the perturbation expansion to make sense. Okay. And you can reformulate the whole perturbation expansion as a perturbation expansion in those parameters, so that you don't have to worry about whether lambda is small or not, right? Because lambda is an unphysical object.
Yeah.
But Harshit, was that your question? That because lambda is
Yeah, I was asking that.
yeah,
Uh,
that so
yeah, if
here
we
it
try to
looks like
relate
you're
lambda
expanding
and
in terms
the
of
physical
something that is
parameter,
infinity. Okay. But that's not the way. I mean, you can avoid that by reorganizing the perturbation expansion.
okay, yeah. And that's one more question. The relation that we've got for the physical mass and the parametric mass, uh, is that a real equation? I mean, does it have to be a real equation?
Oh, whether you can get a
A
imaginary
complex
value from here.
number and yeah.
Okay, in
No, we
perturbation
can get
theory,
imaginary values, but I mean, the terms in sigma can contain imaginary terms.
yes, they can. Okay, but in perturbation theory, right, what you will find is that this mass is real. Okay. As long as the particle refers to a stable particle, right? Sometimes you may find that the particle is not a stable particle, in which you can get a complex imaginary part, but that has its definite interpretation. Okay, unstable particles, okay, their masses have an imaginary part, because that basically reflects the fact that the unstable particles can decay, right? They are not infinitely long lived.
Yeah.
Okay? So their Hamiltonian effectively has an imaginary part, okay, or not the full quantum field theory Hamiltonian, but their effective Hamiltonian has an imaginary part, which tells us that they can decay in time. So unstable particles indeed can have imaginary parts in this. Okay? But as long as you have a stable particle, the lowest mass particle, for example, in the 5 to the 4th theory that you are considering, right? There we do not have imaginary parts, because the phi is the only particle in perturbation theory, right? And that's the lowest mass particle in the theory.
Okay. Yeah.
So in order for it to have an imaginary part, right, the particle has to be able to decay into something, right? That means there must be some other particles which are lower mass than this.
Yeah.
So
Yes, go ahead.
in some like higher some other representation theory of some Lorentz algebra, maybe not the Dirac equation or anything, but
Yeah.
some other representation, can we have fields which are non-linear in the creation and annihilation operators, like some a dagger square, like right now we have some simple expressions like for phi tilde p, the Klein-Gordon field in the momentum in the Fourier basis, we
Yes.
simply have some a plus a dagger
Yeah.
form.
Well,
So
see,
when we
phi being written as a plus a dagger is a specific property of the free theory, right?
yeah.
In the interacting theory, it is not true.
Yeah, I'm still talking about free theory, that in a free theory of some other field, when we actually try to write the Hamiltonian as some a dagger a.
Yeah.
we have to substitute fields as some complicated functions of A and A dagger. Right now, the expression is simple, like as simple as the harmonic oscillator case.
Yeah, okay. So the free theory is defined to be the ones where the Lagrangian is quadratic, and the phi is a linear function of A and A dagger. Okay. Now you may, you may do something the following, right? Take Klein-Gordon theory, okay, and write phi as chi plus chi square.
Yeah.
Okay, it will look like an interacting theory, right?
Yeah.
Even though the theory is actually free. Okay. And in that theory, of course, when you try to express chi in terms of A and A dagger, right, the relationship would be non-linear, right?
Yeah.
So you can certainly do that, right? But normally, at least in perturbation theory, what we mean by free theory, right, in terms of which you can do perturbation theory, is the one where the theory is simple, and those are typically quadratic theories, right? Theories with quadratic action, and there the fields are really linear combinations of A and A dagger.
Okay.
But what you're asking, if you are asking a question in principle, yes, that's certainly possible, right? And one way to make it possible is to just take a Klein-Gordon theory and write phi as chi plus chi square.
Yeah, then even the 2-point functions, like when we are calculating 2-point functions and introducing in a complete set of states, we'll get contributions from higher multi-particle states and all.
Yes, indeed, right? Chi 2-point function will get contribution from multi-particle states.
Like if this procedure is coherent, like substituting a field phi by some non-linear field chi plus chi square or something like that, isn't there an ambiguity in what we call particles?
No, there is no ambiguity in what we call particles, because particles are the poles in the Green's function.
And that will come out to be the same.
That will come out to be the same, right? If you use chi, for example, right, you can try this. I mean, in Klein-Gordon theory, just replace phi by chi.
Yeah.
Chi plus chi square. Okay, you will get a complicated fine set of Feynman rules. Okay? But the poles, okay, will not change their position.
Okay.
So that's important, right? So the particle spectrum, right, doesn't depend on what field you use to describe the theory, right? In fact, I mean, later on, you will see that there are many theories where the fields that we use, right, do not create particles at all. Okay? In quantum chromodynamics, for example, it's like that. Okay, you introduce quark fields, okay, but quarks are not physical particles. Okay, the physical particles are composites of quarks. And there, if you want to actually calculate the masses of protons, for example, from the theory of quarks, okay, you have to look at composite operators, look at the 2-point function, and look for poles. This is unfortunately cannot be done in perturbation theory, but people use lattice gauge theory, for example, to look for masses of particles this way. So the general principle is that you look for poles in the Green's function, right? The Green's, it doesn't have to be Green's function of elementary fields. Okay, it can be Green's function of composite fields. And the poles in the Green's function contain information about the particle spectrum.
All right.
Any other question?
Sir?
Yes, go ahead, please.
Sir, you have just said that in the chromodynamics, we don't have a particle interpretation. Like quark fields don't have a particle interpretation. Is that what you mean?
That's right, exactly. That quarks are not free, not actually asymptotic particles. You cannot have a free quark in the theory. But quark fields are still useful. The elementary fields that you introduce, right, represent something like quarks, right, which are not actually physical particles. But the theory still makes sense, and you can look for poles in the Green's function to find the physical particle spectrum, right? The physical particles are protons and neutrons, for example.
Yes. So how do we have this quark masses? What we have, like
So,
up quark, down
quark
quark,
masses are basically the parameters that you introduce in Lagrange. Okay? or some kind of renormalized parameters that you introduce in the Lagrangian. That's what you mean by quark masses.
Yes, yes.
But they are not physical masses of any particle.
Okay, because quark field don't have a particle interpretation.
Exactly, because quarks don't really exist as particles.
Okay, okay, yeah. So these masses are actually the measured masses or something that fits to the theory
Exactly.
to predict
So
the
these are
proton
parameters
or neutron masses.
Exactly. So these are parameters that you adjust so that the results are consistent with the experiment, right? But what the experiment that you do doesn't directly measure the quark masses. Right? The experiments always involve protons and neutrons because those are the ones that you can do experiments with. Right? You cannot take two quarks and throw them at each other to see what comes out.
Yes. And sir, one more thing.
Yes.
Just can you go to the last slide?
Last slide. This is the last slide. The previous one. Yes. Okay. This
Yes,
one.
yes, previous one.
Yes.
So you're saying that this MP square will be a series, right? In terms of M and this sigma.
Yes.
Sigma
Exactly.
that you have defined.
Yeah. MP square will be a series, which is here, right? By iteratively solving this, you can get MP square as a series expansion in lambda.
Yes.
Okay? Because you are doing perturbation theory, right? If you are doing some non-perturbative techniques like lattice gauge theory, right? Then you will not calculate MP this way, right? You will basically calculate the two-point function using some numerical method, and then you look for the poles in the two-point function.
So you have said that this will be ultravioletically divergent. So can this cannot be contain infrared divergence? Like
Yeah. So typically one finds that the masses are not affected by infrared divergence. The masses, the divergences that affect the masses are always ultraviolet divergences. Yeah, but that requires some detailed analysis. This
yeah,
relation is not
that is
affected by
very.
infrared.
If
But
we
this is
do
not
the
something you can see immediately.
okay.
Sorry, you had some follow-up question? Go ahead, please.
Yes, I was saying that you tell that if we do this renormalization process actually, then we'll see that this is ultravioletically divergent, not infrared. Is
Yeah,
that what you mean?
ultraviolet divergence you can easily see, right? Let's take this diagram for example, right? This is integral d4L over L square, right? There is a single loop which carries the momentum L. So you have a one propagator, so there is a 1 over L square, right?
Yes.
And you have to do an integral d4L.
Yes.
So just by counting powers, so you can see that you have 4 powers in the numerator, right? And 2 powers in the denominator. So this integral is clearly divergent in large L region.
Yes.
So that's the simplest example of ultraviolet divergence that you see in this.
Okay. Thank you.
Okay. Any other question? Okay, so if not, I'll stop the meeting now. And we'll meet next week. I'll let you know whether the Wednesday's class will be a tutorial or whether we'll make it into a regular class. Okay, I'll talk to Samasit and then let you know. Okay, so I'm stopping now.